Hey guys, this is Carrie, and this is lesson 2 from our How Computers Work unit. So if you haven't already, pause now and give the do now a shot. Alright, so let's come back together. We've been talking about how computers work on a really small scale. Well, the smallest scale that you can get is something called a bit. And a bit is a single unit of memory inside of a computer. So we learned last time that your computer has something called a hard drive. And inside of that hard drive, there are a whole bunch of basically slots. And each of those slots could be either a 0 or a 1. Depending on which way a magnet was facing, either facing up or facing down would be 0 or 1, or whether there was current going through that slot would be a 0 or a 1, or whether there was an electron stored in an open cell would be a 0 or a 1, depending on the component that you're talking about. But this right here, that smallest unit of memory, that is a bit. And so a bit is always is either a 0 or a 1, or a bit. All right, now a cool fact about bits that you might not have heard last lesson, because I didn't say it last lesson, is that the word bit, even though it's descriptive because it's a tiny bit of information, it actually comes from combining the words binary and digit, because it's a single binary digit, either a 0 or a 1. Binary meaning two choices. So if you take the by and the it makes a bit. All right, so convert the following number from binary to decimal. Well, this starts to get at a really interesting question. If everything in your computer is either zeros or ones, how can you make a more complex, a larger number than a 0 or a 1? And there's a system for doing that called binary. So the way that binary works is binary is a base 2 number system. And when we say base 2, what that means is there are two choices for each digit. Each digit is either a 0 or a 1. Unlike decimal you have 10 choices for each digit. You have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then you run out of digits, right? So you have to go on to two places with 1, 0, which is 10. Here we only have the symbol 0 and 1. All right, so getting back to binary, let's convert this binary number. So the way that we convert it is we use place values. So we often think about this as the ones place. In normal numbers, this is the tens place. But because this is a base 2 number system, the way we figure out the place values is we multiply by 2 each time we go ahead. So this would be the 2's place. It's how many 2's we have. And this would be the 4's place, how many 4's we have. And this would be the 8's place, 16's place. Whoa, it's hard to be neat here. 32's place, because 16 times 2 is 32. Times 2 would make this the 64's place. Times 2 would make this the 128's place. So now looking at what we have one of these. So we have 128. We have no 64's. We have 132. We have 116 because there's a 1 there. We have 0 8's, 0 4's, 1 2, and 1 1. So maybe using a calculator to put these numbers all together. I don't have a calculator conveniently located. So this would be 130 plus 32 is 162 plus 17 is 149, I believe. Or sorry, wow, that's totally wrong. Let me redo that. 128 plus 2 is 130. Plus 32 is 162. Plus 17 is 179. All right, hopefully I got that right. You guys can let me know if I didn't. All right, so you can turn, and this is what your computer actually does. When it wants to store a number inside of its memory, it takes a group of these values, zeros and ones, and this number represent the same thing. So when you have a calculator program, perhaps it's storing that information like this, and then doing the process that we just did so that it displays the number back to you properly. All right, so let's pretend to be the other part of the computer. Let's pretend a user types in 102. They see it as 102 on the screen. How does the computer see it in memory? Well, it's going to see it as binary, so collections of zeros and ones. So the easiest way to convert this number is to create our place value system. So we have the ones place, just like before, the twos place, because it's times 2 each time, times 2 would be the fours place, times 2, 4 times 2 is 8, 8 times 2 is 16's place, 32nd's place, 64th place, times 2 would be 128th place. All right, and we know we don't have to continue, because if you think about the number 102, you don't need to have any 128s or 256s or whatever comes after that. Okay, so let's make the number 102. So we go from left to right here, and we have to debate, do we need any 64s? Yeah, we need a 64. So if we do 102 minus 64, that will give us, let's see, oh, sorry, I'm forgetting how to subtract. It's really early in the morning here. All right, so this gives us that, 9, 12, 8, and 38, I believe. Okay, so 38, great. All right, cool. So we had 164. It looks like we have still left over 38, so we'll need a 32 as well. So we'll take one of those, and we'll subtract off that 32. This one's a little easier. We get 6. If we only have 6 left, we don't need any 16s. We don't need any 8s. We do need a 4. We do need a 2, because that will make our 6 step. And we don't need any 1s, because it's not odd. All right, so we found that this number, 102, is actually the same number as 1100110 in binary. So when you type 102 into your computer, inside of its memory, it may be seeing that number as something that looks like this. Okay, so we started to ask this question, which is numbers to numbers, binary to decimal. It seems like there's an easy system, or not an easy system, a straightforward system for how you can communicate between those two things. But your computer stores lots more complex images or complex things in its memory, like images. So a black and white image is actually pretty straightforward to represent. We could say in the image below, each row of the image is encoded in a single decimal number. Convert the decimal number to its binary 4-bit representation, and using zeros as black squares and ones as white squares, shade the pixels to create the encoded image. So because we're going to have 4 bits for each one of these, I'm going to just set it up like this. We'll have our place values. So this will be our ones place, twos place, fours place, and eights place using that times 2 rule. And let's see, to make the number 8, we need 1 8 and nothing else. So it looks like using that system, we want black squares for the zeros, so these are all going to be a black square. All right, next step, 12. We need 1 8, 1 4, 0 2s, and 0 1s. So that will be one of these, and then these, oops, these are off. Okay, next up we need to make 14, so we'll need an 8, certainly. We'll need a 4, that gives us 12 total. We need a 2, now we have 14 total because of 8 plus 4 plus 2, and we need 0 1s. So we just turn this light off because it has a 0 there, so that switch should be off. And then next up, to make 15, we need an 8, we need a 4, we need a 2, that's 14 from before, plus 1, 1, and that will give us 15. So all of the lights are on. And so this makes a nice little graphic of something that might appear like a little staircase on your screen if you're making like I don't know, some Mario video game or something where a character had to jump up the squares. Perhaps this is how you could represent the squares that the character jumps up, because you have this lit up. All right, so we're starting to see bits are the basic unit of memory. A single bit is either a 0 or a 1. To store numbers, your computer uses a system called binary, which takes ones and zeros and converts it to normal decimal numbers. For black and white images, your computer can store it as a set of either black lights, which would be zeros, that would be a pixel that's turned off, or white lights, a pixel that's turned completely on, which would be a 1. Today we're going to try to attempt to answer how do we store something more complex like a English sentence or even a single letter. How do we store something like that in a computer's memory? All right, so to get to that question, it's going to take us a second, but let's ask a question that seemingly is unrelated. So you have 4 hats, 3 shirts, and 2 pairs of pants. How many possible outfits can you make? All right, so we're not talking fashionable outfits here, we're just talking outfits. So let's say we were getting ready in the morning and we want to come up with our outfit from the top down. So first we're going to pick from the hats. So I don't know, maybe here we are in our closet and we look at the hats and we've got 4 choices for hats. So we could go any of those 4 directions. I don't think I know enough hat names to do this, but we have 4 choices for hats. So maybe, let's see, what would be some hats? Let's pretend cowboy hat, baseball hat. I don't know, what's another hat? What's a hat? Shoot. Pirate hat. Or I don't know, fedora or something. So then we've got our hats. After that, regardless of which hat we choose, we have 3 choices of shirts. And it's the same 3 choices of shirts for each one, but we can see the diagram branching off further and further. So we could do cowboy hat, yellow shirt or something, or we could do baseball hat, yellow shirt. But now, regardless of which shirt we pick, we also have 2 pairs of pants that we can choose from. So each combination branches off into 2 more. So we can actually create a lot of outfits using just a few articles of clothing, as long as we don't care about those things matching. So let's count how many outfits we were able to make. If we go completely up this route, so the first hat, the first shirt, and the first pair of pants, that would be, let me use a different color. First hat, first shirt, first pair of pants, that would be 1 outfit, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24 different outfits. So that was actually a pretty complicated problem to solve. It took a nice diagram and some counting that was easy to make mistakes with, as you might have seen from my trying to count it. So you might be wondering mathematically, is there an easier way to do this problem? And absolutely, right? So the way I like to think about problems like this is I like to think about it as you're making 3 choices. You've got your hat choice, you've got your shirt choice, you've got your pants choice. And you've got how many choices for your hat? You've got 4 choices for your hat, 3 choices for your shirt, 2 choices for your pants. And you can see that the number of possibilities that you're going to make is 4 choices for the hat times 3 choices for the shirt will give you the 12 choices up till here. And then multiplying again here times 2 because you have 2 choices for each hat-shirt combination. If you do that, 4 times 3 is 12 times 2, that gives you your 24 outfits. And so this is a common trick that or not a common trick, this is a mathematical representation of what we did pictorially. It's not a trick. 24 outfits. So multiplying the values gives you that. All right, so let's take a look at this for bits now. How does this connect to what we were even trying to do? So fill in the table below. Well, with a single bit, we just have 1 slot, and we're choosing either a 0 or a 1. And so that sounds like we only can make two combinations of information. It's either going to be a 0 or a 1 this time, which will be two possible combinations. One is the 0, one is the 1. And if we think about the range of numbers that we can represent, if we have two combinations, that's going to be all of the numbers from 0 to 1, because that is just two different numbers. We can't represent a 2 because we only have one slot, one bit. With 2 bits, it's a little more interesting. The first one is either going to be a 0 or a 1. So similar to our hat problem, here we had 4 choices. Because this is going to be a 0 or a 1, we have 2 choices for this spot. And this is also going to be a 0 or a 1. We have 2 choices for this spot. So it looks like we can represent 4 different numbers 2 times, because what you do at the end is you multiply for each spot, and that gives you the total number of combinations. So the range of numbers we can represent here would be 0 to 3, because 0, 1, 2, 3, well, that's 4 numbers. That's all of our combinations. And we did this yesterday, actually. You remember we said 0, 0 is 0, 0, 1 is 1, 1, 0 is 2, 1, 1 is 3. And that was all of our combinations. All right, well, with 3 bits, let's see what we could do. We have 1, 2, 3 choices that we're making. This is either 0 or 1. So we have 2 choices here, times 2 choices here, times 2 choices here, so 8 total choices. And if we had 8 total choices, well, we're going to use 1 to represent the number 0. 4, 5, 6, 1, 2, 3, 4, 5, 6, 7, 8. It looks like we can represent the numbers from 0 to 7 using those 8 combinations. And that would take up all 8 of them, because we would match up each one with one of these digits. So 1 gets used on the 0, and then we have 7 left over to make the numbers from 1 to 7. So perhaps you're starting to see some patterns here. So try to fill out the rest of the table on your own, and then we'll review it to see if you get it correct. So with 4 bits, you have 1, 2, 3, 4 spots, 2 choices for each of them. And perhaps you're starting to think, well, 2 times 2 times 2 times 2 is getting to be a lot to write. Another way to write repeated multiplication, right, is as a power. So we have 2 to the 4th power, because we're multiplying 2 by itself 4 times. If you plug this in on your calculator, or this will lead you with 16 combinations that you can make. With 16 combinations, we use the first one to make a 0, which would be 0, 0, 0, 0. And then we have 15 left over, so we can go from 0 to 15. The next one, this would be 2 to the 5th, because you have 5 choices that you're making, all of them with 2 choices. That's 32. Let me make the exponent better looking here. 2 to the 5th is 32. So we can represent the numbers from 0 to, well, 1 combination is used for the 0, and then we have 31 leftover combinations. So that would be 0 to 31. 2 to the 6th is going to be 64, 0 to 63. 2 to the 7th is going to be 128, so that's 0 to 127. 2 to the 8th is going to be 256 combinations. You can just check these using your calculator, which would be 0 to 255 for the range of numbers. All right, so our goal today is to figure out a way to represent language in binary. And that's going to be letters. So we'll try to figure out how our computer stores words in their memory. How many combination of bits do we need if we want to assign each letter in the English alphabet, uppercase and lowercase, all common punctuation and mathematical symbols, a unique combination of bits? So this is a problem people had to solve. We had a computer that could only understand ones and zeros, and we need to find a way to convert that to a letter. So let's think about this like we were trying to build a computer from the ground up. So we know we need the capital letters. That's going to be 26 capitals, right? Because the alphabet is 26 letters. We know we need the lower cases. That's going to be another 26. We know we need punctuation. So let's think about common punctuation symbols. We need like a colon, a semicolon, a comma, a period, an apostrophe. I don't know what else we need punctuation-wise. I'm sure we can think of other ones. We know we need a space bar, so let me just put that here. I know it's not punctuation. We know we need a space bar. We also, maybe we want to include numbers in our messages. So we need 10 different symbols from the numbers because we want to be able to put 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 different digits. So let's see what we get here. 26 plus 26 plus 4 or 5, 4, plus 10, 52, plus 4, 56, 66. Okay. So we might need like 66 symbols. And that's just off the top of my head. There are probably symbols that I'm forgetting we need as well. But I think that gives us a pretty good start. So if we go to our table here, we want to come up with a new system. So we use the binary system to convert numbers between normal numbers and binary. We want to find a system that converts between binary and letters. So looking at our table, if we want to make 66 symbols, we need to match up a combination of bits with each one of these symbols. So A will have some representation, B will need some representation, and we'll need 66 possible combinations. One for each of the symbols that we're trying to make. So if we had only one bit, that looks like only 2 combinations, so that would only give us 2 letters. So 1 bit is out. 2 bits gives us 4, we need 66. 3 is 8, we need 66. 16, we need 66. 32, we need 66. 64 is too small, we need 66. So it looks like 7 bits. Because 7 bits gives 128 combinations, and each combination can be linked to a symbol. And this is actually what people did, and they called this system ASCII. So ASCII is the American Standard Communication Information Interchange System. You can definitely Wikipedia this; it's super famous. But the American Standard Code for Information Interchange. I'm not gonna. Well, I'll write that. American Standard Code for Information Interchange. And if you take the first letter of those words, it makes ASCII. All right, so here is something called an ASCII table. And it has, oh, we left off so many symbols. Wow, I didn't even think about those. It has a system for turning a number into a letter. So this is going to be the system that we use. So an interesting historical fact is ASCII actually existed before computers did. So ASCII comes from telegrams. And telegrams were a tool used for sending messages before the internet, before text messages. So ASCII comes from telegrams, and it was invented in 1963 by people. And it was a system for turning numbers into letters. And since we have a system for turning binary into numbers, we can always turn those numbers into letters. And then we have a linkage to make letters from binary symbols. All right. There are some other interesting things about this ASCII table, but let's get some practice with it first. So we want to convert the number 70 to ASCII, or to its ASCII character. So on the table, we'll look up, we'll look up 70 on the table. So 70 is the letter F. So this is an F. 117. This is a lowercase u. Oh gosh, okay. And then the binary here, 111001. you'll notice that this has 1, 2, 3, 4, 5, 6, 7 digits, which should resonate with what we talked about here, where we needed 7 bits to make each character. So zooming in and making the place values here, this is the 1's place, the 2's place, the 4's place, the 8's place, the 16's place, the 32nd's place, and the 64's place. So we have to convert from binary to decimal here, and let's see, we've got a 64 plus a 32 plus a 16 plus a 1. This is 80 plus 33, that's 111. Let me just make sure I got that right. 64 plus 16 is 80, plus 33, nope, I got that wrong, is 113. All right, so let's see what letter that is. 113 is a Q. So we have a Q here. I think I was trying to get an N to make it fun, but I guess I failed and put the wrong characters here. So this is a system for translating between binary and an ASCII. So we've got all of our letters. What should we do if we want to include, oh, this is a big question, right? So in 1963, we may have been focusing on sending messages mostly in English. But of course, as computers have evolved, we wanted to send messages in non-English languages as well. So if you think about languages that use similar alphabets, we have a whole bunch more characters that we need to include. So we have stuff with like accents, A with an accent. We've got A with an accent the other way. We've got enyes. We've got a whole bunch of new characters. And very quickly, you'll notice that we actually start to run out of characters if we use only 7 bits. So 7 bits was 128 characters. So ASCII was actually revised in order to include new characters like these ones in something called extended ASCII. And extended ASCII, because it had an extra set of characters that it was trying to include, required 8 bits. So this would be going to our table here with 8 bits, that'd be 256 combinations. So we can represent 256 characters, letters, symbols, using something called extended ASCII. And the reason why this is called extended ASCII is because it uses 1 extra bit. And so it turns out that this actually was pretty sustainable. It lasted a pretty long time. And 8 bits became a really fundamental number of bits that a computer likes to have. So let's do one example of an 8-bit ASCII conversion. So I don't know, 0, 1, 1, that's 3 bits. I'm just making this up. 0, 1, 0, 1, 1. So 1, 2, 3, 4, 5, 6, 7, 8 bits. So this would be an extended ASCII symbol. And your computer would know to translate this based on the file format. Maybe it's a .word file or a .pdf file. I'm not sure, but it knows based on the format that it's going to be using extended ASCII to translate it. So we get our place values: 1's place, 2's place, 4's place, 8's place, 16's, 32nd's, 64's, 128's. So we have 0 128's, we've got a 64, we've got a 32, we've got an 8, and we got a 2, and we've got a 1. So we have 64, 32, 8, 2, and 1. These two make 40. This makes 40 plus 64 is 104, plus 3 is 107. All right, so let's see, 107, this would be the letter K. So we've got a system now for translating between 8 bits and extended ASCII, or in characters. What is a byte? How many unique combinations can be made using 1 byte of data? Okay, so here we go. We said that ASCII was great. 7 bits for 128 characters seems like a lot, and it's really nice. But we very quickly needed to upgrade our system so that we had 8 bits, which would be 256 characters. This is a lot of possible symbols, and so it turns out this lasted for a long time and became a fundamental unit of memory. So we started to call a group of 8 bits So in your computer's memory, I like to think about these as collections of 8 bits. So each one of these would be a 0 or a 1. Let me just make sure we have 8. 1, 2, 3, 4, 5, 6, 7, 8, 9. Oops. So 8 bits. Because this represents one letter or character, it was useful to start to have a name for groups of 8 bits, because every group of 8 bits was going to be converted to a letter, like K here. So 8 bits equals one letter, and so we call 8 bits 1 byte. And you've perhaps heard of the word byte, right? When you think about files on your computer, they're stored using kilobytes, which is 1,000 bytes, because kilo means 1,000. So 1,000 bytes would be 1,000 letters worth of memory. A megabyte is 1,000,000 bytes. So 1,000,000 of these 8-bit combinations, and that would be 1,000,000 letters worth of memory. Or gigabyte even. It's a lot of bytes. It's a lot of letters. So if you think about the storage on your computer and how much the files take up, 1 billion bytes is a gigabyte. And that's 1 billion of these things, which would mean 1 gigabyte is 1 billion times 8 billion bits. So a gigabyte has 8 billion zeros and ones. That's remarkable. All right. So of course, like a final question continues, right? Language has continued to evolve over time. And perhaps like our favorite version of language evolving is symbols called emojis. So if you type in an emoji, that symbol is stored as a collection of ones and zeros, and somehow that gets converted to something like a smiley face, or a hospital, or an apple, or some other symbol. And we need a way then to convert between binary and emojis. Or if you think about calligraphy-based languages, or languages that have different alphabets from English, we need some binary combinations for those as well. So the symbol, or the language, or so ASCII has evolved to another system as language has progressed called UTF. And let me just look this up real quick. UTF stands for Unicode Transformation Format. And UTF-8 is the most popular version of this. And it's another tool that takes a collection of bits and turns those into letters. And perhaps, this would be a big reach, perhaps you remember back to our first days of programming, we actually would have to specify in a meta line of code that we wanted Safari to use UTF-8 in order to translate our web page. And if we didn't specify this, Safari accidentally translated the ones and zeros instead of to emojis to those crazy symbols. It looked something like, I don't know. It looked like crazy symbols. The reason why is Safari wasn't using the correct tool to translate between the ones and zeros in memory to the emojis. So the rest of the lesson is going to be practice where you're working with ASCII. ASCII is still a current basis, because even within UTF-8, ASCII is incorporated. So ASCII, just to review it, we're going to be using 8-bit representations. 8 bits is another word for 1 byte. And if you think about 8 bits, 1 byte, you can go back up here and you can figure out how many combinations can you make with 8 bits. All right, so guys, please do your best to translate or to do problems 1, 2, 3, and 4 here. There are some secret messages. I hope that those come out to be words. I think that was my intention, but I wrote this lesson last year, so it's not super fresh in my memory. Anyway, please send pictures of your lesson once it's complete, and any questions that you have.